Okay, let's do a second example of chemical formula determination and isomer determinations. So in this example, we're given the following mass spectrum. Notice that we have actually three peaks that appear at the highest mass to charge ratio. At first look, you might be tempted to say that 59 is the M plus peak because it's the one that's farthest to the left out of everything closest to the right side of the spectrum. But the truth of the matter is that it isn't. And the reason we know that to be the fact is because if this is the M plus peak, the M plus plus 1 peak should automatically be smaller, a lot smaller than the M plus peak. And what you can see right here is that the mass of 59 is not bigger than the one at 60. Therefore, the mass at 60 must actually be the M plus peak. And then you can see that right next to it, at 61, we have a mass that is a lot smaller than the mass at 60. So that works out. Okay. Notice that the percentage of the M plus peak is not equal to 100%. So we're going to have to rescale it back to 100%. And since this is equal to 4.2, we're going to divide by 4.2 and multiply by 100. Also, we will take the percentage at M plus plus 1 divided by 4.2 and multiply by 100 to get 2.2. Knowing that value, if we divide 1.1 for the percentage of the M plus plus 1 peak, we will get the number of carbons, which is equal to 2 in this case. All right, now the mass, the M plus mass was 60. 60 minus 2 carbons, which are equal to a mass of 12, right? So 12 times 2, that's the overall mass of 2 carbons. That tells us that there's 36. Now, at first you might say, okay, we're done. We got the number of hydrogens, except that this doesn't work out because 36 is more hydrogens than you could possibly fit into carbons based on the 2m plus 2 formula. All right, so then this is the deal. There are some elements that are missing. And we might want to look at the m plus plus 2 peak, except that we don't have any. And so that kind of creates a problem because if we don't have an M plus plus 2 peak, then there is no bromine, there is no chlorine, and there is no sulfur. However, the absence of the M plus plus 2 peak does not automatically negate the presence of oxygen. So we're going to see what happens if we start introducing oxygens into the formula, and we're going to take a look at the mass. All right, so we'll start with one oxygen. So we have the overall mass of 60, which is the M plus mass, minus 12 times 2 because of the 2 carbons. Let's subtract now one oxygen out of it. An oxygen has a mass of 16. If we carry out the multiplications followed by the subtractions, we end up with 20 hydrogens, which still is way higher than you can put in 2 carbons. So this still doesn't work out. But notice that this value is just a little bit higher than 16. So this is prompting us to the idea that maybe there's not just one oxygen, but rather 2 oxygens. And if we do that, now we end up with a value of 4 for hydrogens. And 4 hydrogens you can absolutely place with 2 carbons. So this works out. Having 2 oxygens in the formula gives us the correct value of 60 for the M plus peak and the correct number of hydrogens, or at least number of hydrogens that does not violate the maximum value. All right, so let's take a look and see what type of isomers we can determine and come up with this formula. So we turn our attention to the IHD formula. For 2 carbons, if we plug the 2 for N, 2 times 2 is 4, 4 plus 2 is 6. The equivalent number of hydrogens, we have 4 oxygens we ignore, so it's only 4. So we're going to have 6 minus 4, which is 2. 2 divided by 2, that's equal to 1. Okay, so this is telling us that because the IHD is equal to 1, we're either going to have a double bond or we're going to have a ring in the molecular structure of C2H4O2. So let's start with the premise of the double bond. And let's say that the double bond is between the 2 carbons, in which case we're dealing with alkenes. Okay, so first we draw the alkene, so carbon-carbon, so that takes care of the 2 carbons. Now we need to bring the oxygen. So we could place one oxygen on this carbon. And notice that on that oxygen, since it's terminal, I need to add a hydrogen to ensure that the oxygen ends up with 2 bonds. Much like neutral carbon must have 4 bonds, neutral oxygen has to have 2 bonds. Now the second oxygen can be placed here. And now notice that I've drawn this in opposite sections of each other from the point of view of the double bond. This is the trans configuration, so we could also draw the cis configuration for that same molecule. But there is no reason why we would have to have the 2 oxygens on separate carbons. We could place them both on the same carbon, in which case we end up with this geminal diol, which is a possibility. It works out. For all of them, notice once more that we have 1 hydrogen on the oxygen, so that we end up with 2 bonds on each one of the oxygens. All right, now there's one more possibility, and that is drawing the carbon-carbon double bond. We have the oxygen bound to it. This oxygen needs to be bound to something else to have 2 bonds. So let's have that bond to the second oxygen, in which case we're drawing a peroxide bond. Now this oxygen here at the end is terminal, so it must have a hydrogen on it to have 2 bonds altogether. All right, so this type of molecule also works out because everything has the correct number of bonds. We have the correct number of hydrogens. In fact, look at this. Here we have 2 hydrogens, here we have 1 hydrogen, and we have 1 more hydrogen over there for a total of 4 hydrogens as depicted by the formula. So simply following what the IHD told us to have on the formula is giving us the correct number of hydrogens. Okay, now what happens though if the double bond takes place between one of the carbons and one of the oxygens? In other words, if we have a carbonyl functionality. Well, we still have to have 2 carbons and we still have to have 2 oxygens present. So we can place the second carbon bound to the carbonyl, and we could have the second oxygen bound to this last carbon. Okay, and this works out. So we have 1 hydrogen over there, we have 2 hydrogens here, and we have 1 more over there. So 1 plus 2 plus 1 is equal to 4. But alternatively, we could have not just the second carbon bound to the carbonyl carbon, but we could have the second oxygen also bound to the carbonyl carbon, in which case now we have a carboxylic acid. Another alternative is that we still do have the oxygen bound to the carbonyl carbon, but instead of having the second carbon bound to the carbonyl carbon, now we combine the external carbon to ensure that this oxygen, to the external oxygen, to ensure that the oxygen here has 2 bonds altogether. And over here we have 3 hydrogens. Here we have 1 hydrogen. Nothing else has hydrogens, so we end up with 4 hydrogens again. Okay, and the last thing is the rings. We have 4 non-hydrogen atoms present in here, so we could draw a square molecule and we can place 2 oxygens in opposite corners, or we could place them next to each other. And if you look at the number of hydrogens, this has 2 hydrogens, that has 2 hydrogens, 4 hydrogens. 2 and 2, 4 hydrogens. And the oxygens in either situation have 2 bonds each, so they're happy the way they are. But we could also be dealing with a 3-member ring. You could have your oxygen content within it, right? So oxygen bond and 1 carbon, which means that the second carbon will have to stick out from the 3-member ring. Or alternatively, we could have 2 carbons on the 3-member ring, only 1 oxygen, in which case we'll have to have the second oxygen sticking out of the 3-member ring. And since that oxygen is now external, now we need to place a hydrogen on it to ensure that it has 2 bonds. And if we count the total number of hydrogens, we have 2 over here, we only have 1 there, and we have 1 more there. So 2 plus 1 plus 1 is yet again equal to 4. Okay, so that's the story if indeed we have 2 oxygens on that sample. But let's go back to the original premise. The premise that the n plus peak is an even number. Because that's even, instead of having oxygens, we could actually go with the premise that, well, if this is an even number, maybe we have an even number of nitrogens. And perhaps that number is not equal to 0, like it was in the case where we selected 2 oxygens, but maybe it is 2. Now it's important to notice here that because the n plus peak is even, you have to have an even number of nitrogen. So the possibility of having 1 oxygen and 1 nitrogen is not a possibility, because you must have two nitrogens if the value is even right here, right? You could also have four, right? The value of nitrogens must be even if this is even. So you cannot have just one nitrogen or three nitrogens or so on and so forth if this value is even. So we're going to have to add the two nitrogens in here. The value of nitrogen is 14 for its mass. 14 times 2 is 28. We have the two carbons with a mass of 12 each. Subtract that from the mass of 60, which is the N plus mass, and this gives us 8 hydrogens. Now, first look, having the two carbons and two nitrogens with 8 hydrogens may look like this is not good, right? Because we're now above the value that we can have for uh, two carbons. Two carbons can only accommodate 6 hydrogens. Here's where you must remember the rules of the IHD formula, specifically that for every nitrogen or phosphorus atom that you have to subtract that amount of hydrogens from the total. So here we have 2 nitrogens. Subtract 2 from 8, that's going to give you 6. And 6 is the maximum number of hydrogens you can have on carbon. So this actually works out. This is good. Okay, so let's see what happens. So C2H8N2. Once again, we already determined that this is the maximum, right? So this tells us that we're going to have no multiple bonds and no rings because the IHD is going to equal 0 specifically. And you can do the calculation to satisfy your curiosity. But with an IHD of 0, having no multiple bonds, no rings, well, let's see what the possibilities are. Let's look for molecules that do not contain nitrogen-nitrogen bonds. One possibility will be the following. We have two carbons over here and we also have two nitrogens. Now notice that the nitrogens are terminal. So now we must ensure that the nitrogens contain two hydrogens on each of them so that we end up with 3 bonds on nitrogen altogether, right? Each hydrogen is meant to have one single bond to nitrogen. So having two hydrogens, that's equivalent to having two NH bonds present. So 3 bonds altogether when you consider the nitrogen-carbon bond. And this is basically the idea. You want to have 2 bonds on oxygen. You want to have 2 bonds on sulfur for them to be neutral. You want to have 3 bonds on nitrogen for it to be neutral. You want to have 4 bonds on carbon for it to be neutral. All right, another possibility would be to only have one carbon separating the two nitrogens. Now, what that would mean is that we will have to place the second carbon on one of the nitrogens separately. So I'm placing the second carbon over here. Now, notice that this nitrogen contains now 2 bonds, one to the carbon on the left and then the second one to the carbon on the right. But it still has to have 3 bonds altogether. That's why I'm placing a hydrogen on that nitrogen. Whereas the nitrogen over here is only bound to one carbon, this carbon right here. It still needs to have 3 bonds, so that's the reason why I'm putting 2 hydrogens on this nitrogen. Okay, now to be sure that this is correct, we need to count the number of hydrogens to see if it even matches up with what we have here. All right, so we have 3 hydrogens here, plus 1 more, that's 4, plus 2 more, that's 6, plus another 2, that's 8, and bingo, that's the number of hydrogens that we have in the chemical formula. One more thing that we could do is have the 2 nitrogens bound to the very same carbon, in which case the 2 nitrogens will have to have 2 hydrogens bound to it so that they have 3 bonds altogether. And then the second carbon is just sticking out, just by itself. Altogether, this carbon has 3 hydrogens. This only has 1. 3 plus 1 is 4. Plus 2 is 8. Plus 2 is 6. Plus another 2, that will be 8 as well. Okay, so that's all the possibilities where there is no nitrogen-nitrogen bonds. Now let's see what happens when we do have nitrogen-nitrogen bonds present. Well, one thing that can happen is that we could have a carbon on one nitrogen and the second one on the second nitrogen, in which case both of the nitrogens already have 2 bonds, which means that we only place 1 hydrogen on the nitrogens to ensure that they end up with 3. The other possibility could be that one of the nitrogens has both of the carbons as methyl groups, and the second nitrogen, the one here on the left, has no carbon bound to it, right? So we need to now add 2 hydrogens to that nitrogen to ensure that it has 3 bonds, whereas this one right here doesn't require any more hydrogens because it already has 3 bonds. And the other possibility would be that instead of having 2 methyl groups on this nitrogen, we could just make that an ethyl group, right? So attach this carbon to that carbon, you end up with an ethyl group. But then what that means is that this nitrogen now only has 2 connections to carbons or nitrogen. So we need to add 1 hydrogen to end up with 3 bonds. And the nitrogen over here only has 1 connection, so we need to add 2 hydrogens to end up with 3 bonds. Okay, so that takes care of that example. Both of those situations, having the 2 nitrogens in one or the 2 oxygens, are valid answers for that type of problem. In the absence of additional spectra, you would not be able to tell which one is the correct answer. So you will have to give both of those things as potential answers. In the next video, I'm going to show you a few more examples to solidify the idea of going from the mass spectrum to the formula and going from the formula to the actual structural formulas and the various isomers. So see you in the next video.